Oh, hello, good evening. Happy, was this March? Yeah, March, right? Yeah. Hello, YouTube. Welcome to Central Ohio.NET Developer Group. Thanks for coming out. This should be a good one. I'm really excited to catch this talk tonight. Just our normal announcements here. We are live on YouTube. Our past meetings are also streamed and recorded, so you can check those out at our channel with our fancy full URL from having over 100 subscribers, so yay, go us. Let's see, we do ask that you can consider the bandwidth here as we are streaming this, just so we have a good experience for those watching remotely. And yep, there we go. Sorry about that. Thank you, Improving, for hosting us and for the content tonight, and of course the Donato's Pizza and drinks. Always appreciated. This is a great space to be meeting in, and we are thankful for it. Thank you also to JetBrains for being our sponsor this month. I believe we have at least one license to raffle off tonight. We might actually have two. I will be checking on that later on from an unclaimed one. But we'll be raffling that off at the end tonight. So just tooling licenses there. And just some other groups in the area. The Central Ohio Azure group is still meeting every second Monday of the month. You can find them also on Meetup. We also have Columbus JS starting up again. I think that's the first Wednesday. Yes, the first Wednesday of the month. There's going to be some interesting projects being demoed this coming Wednesday. It'll be a lot of fun. So I'm looking forward to that. CBus data is still active as well, formerly called CBus Pass, but I guess that's just more data than passes now. And then Star Trek. So Star Trek registration is still open for the Star Trek conference. That will be in May, early May. It'll be a lot of fun. So talk to your organization, see if you can get approval to get some tickets. But you can still register. Go out to StarTrek.com. It's always a lot of fun, and they give you wonderful nerdy T-shirts that don't confuse anybody at all ever. So it's kind of my default around the house attire. Our schedule for the upcoming year is a lot more filled than it was last year. So kudos to those who volunteered to speak or reached out to other people. It's really appreciated. This month we have Gregg talking about design patterns and anti-patterns for Azure applications. Next month we have Roll Your Own Home Security with .NET, Raspberry Pi, and Azure with Heath Murphy. And then Barrett Blake is going to be talking to us in May about an introduction to Blazor for C# devs. I'm really excited about that one. And then Mel is talking to us about coding with others from a distance using, Visual Studio Live Share? Is that the name of the project? I can't remember. That one always slips my mind. So that's going to be really fun. And then in July, we are going to be opening it up for lightning talks as always. So if you have something that would be interesting to talk about or demo in 10-minute slot, be thinking about that now. We'll open that up in a few months for submissions. But I'm already thinking about some things I might want to submit. And we have 3 openings for the back half of the year. So if you know anybody interesting who you might want to have here, any interesting topics, just reach out to any of us on the team, and we'd love to investigate where we can slot them in. If you're looking to help us out on social, organizing, anything else you might be interested in helping us with, let us know. Just talk to Alan, myself, Sam afterwards, and we'd be happy to chat with you about that. And yep, there we are, Alan, myself, Sam. So cool. With that, it's all yours. Thank you again for speaking. Round of applause. And I will give you your HDMI.
We haven't seen the top yet, so no applause.
Well, there's additional applause afterwards as needed.
We'll see.
There you are.
We'll see. Very good. Well, I appreciate everybody coming out with the Sweet 16 games starting here in like 20 minutes. I appreciate the investment of your time.
Yeah, that's probably a good idea.
All right. So this is design patterns and anti-patterns for Azure applications. Really what we're going to talk about, pretty simple from a... Okay, no, everybody's going to fall asleep, myself included. So what we're going to talk about today, pretty simple. We'll do speaker introductions. Full disclosure, this is a presentation that my colleague and I put together and generally do as a 2-man team. So Chris Steele, for those of you who know him, my colleague in Columbus, but he couldn't be here tonight, so you're stuck with just me. So I'll give you a really quick presentation overview, and then we'll jump into some patterns and anti-patterns, a quick wrap up, and then any Q&A. All right, so as I mentioned, we've got two people on the slide. It's only me on the left there. So my name's Gregg Flagg. I'm a director of consulting with Improving. I am based in Cleveland, but am down here in Columbus quite a bit. I've been an architect and in the tech industry for 25 years or so, probably more than that. Areas of expertise really around hyperscale cloud systems, did a lot of work in the connected vehicle and IoT space, and just solution architecture in general is sort of a passion of mine. Prior to coming to Improving, I was at Microsoft for about 14 years or so. All right, so what are we going to talk about? So why did we talk about patterns, right? So what is a design pattern? As we were putting together the content for this presentation, I actually looked at a lot of definitions out there, and the one that I settled on that I thought was the best in terms of being both concise and really highly accurate is a design pattern is a common solution to a recurring problem, right? So we as developers face the same category of problems constantly, right? But our natural inclination a lot of times is to resolve it, right? We love to build stuff, so we want to kind of reinvent the wheel. So the idea around patterns is that they form at different levels, right? So there's patterns at the architectural level, there's patterns at the design level, and there's patterns at the coding level. And our idea around this talk was really to give you a flavor for each of these patterns, right? Or each of these types of patterns. There are a massive universe of patterns out there going back. The research goes back, 40 years back in the COBOL, Fortran days. But there are some that I think are more interesting than others, and so we kind of picked out a few that we thought were impactful. But the idea is certainly not to cover, or even scratch the surface of what the universe of possibilities that are out there. And even though we named this talk around Azure, and which sort of implies cloud, it really, a lot of this stuff is not specific to Azure, right? Equally as applicable on AWS or GCP or insert cloud here, and in some cases also applicable to on-prem systems, right? Some of this is just about good system design. And then patterns versus anti-patterns. So just as much as here's a pattern for what you should be doing, there's also these things that okay, this is a thing that we see a lot that you shouldn't be doing. And the industry roughly calls those anti-patterns. The other interesting thing, if you followed this space for a while, or you're old like Mike and me, is that things that used to be patterns over time have become anti-patterns, right? So really interesting sort of, this is the recommendation today, but that, with the asterisk that it doesn't necessarily mean it's the recommendation tomorrow. All right, so roughly what we'll cover, I kind of went through this already, some of our favorite and not so favorite patterns and anti-patterns. And then the idea is for those of you this might be a new topic for, I'm sure there's probably a lot of people who really know this space, and maybe you guys can come up here and cover some of these slides for me. I'm not used to doing the whole 45 to 60 minutes by myself. Just to give you an idea of what's out there. The other interesting thing I think, as we've been working in this space for a long time, is that a lot of what you're going to see is not super novel, concepts. You're going to look at it and go, well, maybe I didn't know that there was a name for this thing, but this is something I'm already doing, right? And it kind of helps to frame up that I've been on the right track when I was thinking about this problem, and there's other folks who have experienced the same exact thing. And now I know some keywords to go and search when I want to find out some more about it. And really, just kind of spark that desire if you're new to this space and man, this is cool stuff. There's a lot of writing out there. We'll talk about that a little bit in the wrap up too. So that's it. And any questions or comments or thoughts before we get started?
Pretty long.
That was it. Yeah, tip off on the Michigan State game's 6:30. So I'm gonna try to see if I can. Anyway, all right. So. Patterns and anti-patterns. We're actually going to start with an anti-pattern. And so this one, we've named the Synchronous IO Antipattern. So, news flash here on this bullet point, systems can be subjected to unexpected heavy load. This is really even more applicable in the cloud world, right? When you've got a lot of internet-facing endpoints and you very little control, maybe a little bit different if you're running an on-prem solution, that's on your internal network, only VPN'd in users can hit it. You probably feel a little bit better about what the burst of traffic you might actually expect. when we talk about cloud systems, right, we always talk about in terms of horizontal scalability, right? We can still scale stuff up the way we did on-prem, like, okay, the database server is running slow, what do? We build a bigger database server. You can still do that to a certain extent, but really the bang for your buck in the cloud world is horizontal scalability, right? Lots of smaller things partitioned out. But synchronous things are the sort of enemy of horizontal scalability. So one of the things I would challenge you to is Azure, and in general also our mental model is that we kind of work in a synchronous fashion, right? We ask something, we make a request of something, and we're expecting an answer back, right? It's kind of the normal models we interact with as humans. It's the way we sort of build systems. So as you're designing systems, as you're writing code, always be asking yourself, can I make this asynchronous? Does this really have to be synchronous, right? Do I really need the response right now? And sometimes the answer is yes, right, of course, but ask the question. And so, again, we're talking both at the design level and at the coding level. So there's building in asynchronicity in your design, but also when you're actually coding it, right? And they're related, but not necessarily the same thing. And just be especially cognizant of any time you're making an IO call. So that's like, making a database call, making an API call, reading from a queue, blah, 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 et cetera, et cetera. Those are always potential culprits for, man, if I do this in a synchronous way, it's probably it might manifest itself as a bottleneck. So be thinking about that. Anytime like you're writing that ADO.NET stuff and you're hitting the database, think about asynchronous. So really talked a lot about this already. Part of how do we solve it, and this is really the format that we use for most of the slides, right? Present what the problem is, and then present how the pattern or anti-pattern addresses, try not to fall down, presents the solution. So always be thinking, what can I make asynchronous? And then this one, like, I struggled with whether I was going to put this on the slide or not, because I mean, it seems like, yeah, everybody does this, but not everybody does do it, right? So take advantage. Modern languages like C# and frameworks like .NET and Java, I mean, have lots and lots of this stuff built into the framework level, right? So take advantage of it, but make sure you're doing it right? So that there's a point here. Actually, I'm going to skip ahead here, right? So when folks start thinking in terms of making their code base asynchronous, they think about like, we're a .NET users group here, so it's like I'm just going to go and I'm going to write like 1,000 async and await keywords and I'm paste them everywhere in my code, and then things are going to be great, right? We had a poorly performing system, wrote a lot of asyncs and awaits, and now we have a great performing system. Yeah, I know. I see some smiles. I know that, like, yeah, I've seen this movie before. I know how it ends. There's no guarantee that that is like the silver bullet for making your all of a sudden a poorly performing application perform like a champ, but it probably is a good first step, right? And the performance engineering is always about like peeling the onion, right? So it's like you don't know what the next bottleneck is until you peeled the first one off, and then you're like, oh, and then sometimes it moves, right? And then one thing else to call out is I'll actually see a lot of developers who are really comfortable when they're making like framework level calls. They're really good about knowing like, yeah, I'm using async methods, I'm awaiting on them, right? But maybe they forget when they're writing code that might be reused across, maybe it's across an organization, maybe it's open source, maybe it's whatever. Keep in mind that you need to provide async and real async, right? Like real async methods, not just named async. So one of the things you'll notice about this talk is that we're going really fast. We kind of went back and forth about like, should we do fewer patterns and go like really, really deep, or should we do more patterns but at like a less level of depth? And that's a little bit where we landed on. I've said this, I've given this talk multiple times, and I always said like, each one of these patterns that we talk about could probably be an hour talk in and of itself, right? So the idea, we erred on the side of giving you a flavor across different levels and different patterns. But you guys let me know after the talk if that was the right call or not. Certainly open to feedback.
Are your slides going to be available there?
Yes, that was what I was wondering too.
Yeah, absolutely. Sure. Yeah, there's nothing in here that's proprietary. I don't think.
Probably comment on the meetup and put the link there.
Okay, cool. Absolutely. All right, so now we started with the anti-pattern for synchronous IO. And so the idea is that this pattern sort of, what's the term? So this pattern will actually, is one of the ways that we actually help when we have a synchronous IO problem. So what is the problem that we're going to address with the queue-based load leveling? Right, so this is, again, a very obvious statement. Any of your applications that you write, especially ones that you deploy to the cloud, are going to be subject to intermittent heavy load and unexpected intermittent heavy load. Right? It's a rule of thumb. You always, like, that's a tenet that we don't know how much traffic we're going to get. We might think we know. We think we modeled the user behavior like really well. How many people have ever gotten user behavior right up front? Like, yeah, do we know what users do? Nope. And especially, and then, you know, we've got bad actors too, right? So in addition to like legitimate users doing dumb stuff, we've got people intentionally doing bad stuff against our apps all the time, right? You spin up a new SQL Azure instance in the Chinese data centers. You will see brute force SA attacks in 30 seconds.
Wow.
So, again, any sort of, you know, external facing stuff, right? Anything that's IO bound is always going to be subject to these bursts of patterns, right? And unpredictable spikes. You know, we're generally pretty good at scaling systems when we have predictability. Like, we know exactly, like, these are our peaks, right, over time, and we've learned the system's been running a long time. We know that on Fridays that are our payday, you know, our online banking system gets hit much harder. That's all cool, but we have also ones that we did not expect at all, right? We did, let's say, you know, marketing did some massive marketing campaign for your website, and it was more successful than any of the projections, right? You might come in the next day and go, man, it fell over. So, and what happens when you get these, right? It's timeouts, it's throttling, it's degraded response time, it's all the badness, the things you don't ever want if possible. And really, you know, it's not necessarily always the case that it's just heavy load, right? Because again, you know, with autoscale and Azure and stuff, you can generally respond to that, but it's like the concurrent and unexpected nature of it that hurts you. So I think we've all been here, seen these symptoms before. So what's a possible solution to it? And it's all in the name, right? Queue-based load leveling. Really what you're doing here, it's just as simple as, you know, you've got a client and you've got a service over here. What you're doing is introducing a queue in the middle of it, right? So you're breaking that synchronous, so going back to the last pattern, breaking the synchronous nature of it. And so the client now, instead of directly calling the database or directly calling that externally hosted API, the caller is just putting messages on a queue. And he can do that just as fast as he possibly can, right? I mean, it doesn't matter. You could have a massive spike, you know, a burst of 10,000 concurrent requests, and put them all on the queue. And then what happens, right? So instead of actually then picking up those messages and processing them as fast as they're coming in, you're using some form of load leveling at that side. So you're introducing something in between there. And like Azure functions work like wonderfully for this purpose. Right? So you put an Azure function that has a service bus trigger. It pulls messages off of there. You kind of have to know, okay, what is the, you know, what's the maximum rate I can actually issue these against my database or against my vendor's API. But then you can use all the goodness of Azure, right? All the limits around how much it will auto scale stuff to tune it in and say like, okay, if we know our SLA with this external API, you know, because we signed a contract, they said, we can't do more than 100 requests per second. Well, we can tune that then, right? We can observe it and say, okay, I know if I have 6 instances of my Azure function scaled out horizontally, I'm getting like 98, 99 transactions per second. So, yeah, so again, pump as much stuff in as fast as you can, but only read it off at the rate that's appropriate for your system. And so then, of course, that's where the load level comes in, right? So it comes in, it's all jagged and spiky and bursty, but on the outside, it's nice and smooth, right? It's at a rate that you're controlling, not whoever's in queuing all this stuff. Was there a question? Or no? Sorry. Oh yeah, you got a question.
Does that mean like in order to utilize the queue-based load leveling pattern, would you need like some load balances on there in order for that to effectively work?
You know, it depends. So this is again a pattern. Right, so the actual implementation details of how you build it could look very different, right? So I kind of mentioned just using like service bus with Azure Functions. That's one implementation, but it's certainly not the only one, right? So I know that's a wishy-washy answer, but it depends. Yeah.
So is the queues coming and going at that point?
No.
Like what color places it on the queue, and then how do they get their return? Oh, okay.
Wait for it. Oh, man, he's teeing it up. All right, save all questions for the end. No, but okay. So almost every one of the slides, we also have a caveats. At least one, because none of this stuff is perfect, right? And none of it. This all sounds like super easy, right? But it is. Yeah, none of it's super easy.
That's the asterisk.
Yes.
For sure.
Yes. Exactly. So here is it. And to your question, this pattern is inherently one way, right? This is all about I am doing something that I don't need an immediate response for. So there are other patterns for how to then achieve this, but with request response semantics, right? So, and really what it is actually just turning it like on its head, right? So you have one queue that's going on the request side and another queue that's coming on the response side. And so that guy that enqueued the message originally enqueues the message, but then waits on the response from the response queue, right? And there are pitfalls there too. This is not like it's not a panacea, but it is one way to achieve something that looks like pseudo-synchronous. Okay, and then I think we probably covered this one, or like again, sounds super simple. Getting the rates actually correct is not simple, right? You might think you did, and it turns out you tuned it wrong and you still tipped over whatever you were trying to protect with this pattern in the first place. So test, and retest. Yeah?
I don't know, maybe this is coming down the road, but I thought to still mention that, these could have quite some liabilities, right? Can you guarantee, so you're replacing calling stack with something else. So for instance, can you guarantee exactly when delivery? Are you prone against repetitions? Are your operations how important? Does your queue has a recovery? Is that recovery consistent? So there's a whole host of problems here, right?
Yeah.
And
Wait, I'm going to ask you. So I have a slide on eventual consistency.
And that
a lot of what we're
You'll eventually.
I will get to it eventually. Bear with me. I love the words that you're saying, though. These are all good things. Good things to consider. They're bad things, but they're good things to consider, right? Okay, love it when the audience does my presentation for me. All right, so now we're going to switch gears a little bit. Very different pattern, not related to what we were just talking about. But this is the idea of a claim check. And so in terms of, we were talking about, let's say we're talking about like messaging systems. This might be IoT, right? It might be something where, let's say the system you're building, anything that has to like manage large payloads. So it could be user updates or profile pic, right? In the IoT scenario, maybe it's a CT scan that's sending, a really massive image file or set of files that eventually get to a human radiologist, et cetera. So very common, right? We build these kinds of systems all the time. So your first instinct, if this is like the very first queuing system, messaging system you've ever worked on, your first inclination might be to actually just try to shove all of that data in the payload of the message. And I will be honest, I'm not proud to admit it, but I will admit it. In my first system, I had a hand in crashing a very large, very complex MQ series system in the 90s because I did this, right? Now, what was big back then is not big now, but it was still too big. And bad things happened. So you might say to me, like, Greg, the Microsoft documentation says that a service bus premium message can be 100 megs, and it does, and it can. But just because you can do a thing doesn't mean you should do a thing, right? So you have to trust me on this one that this will, don't do it. Even though there's a whole history behind why Microsoft raised the limits to be so huge. And I guarantee your scenario is not the one, right? So without going into the history there, don't do it. It's going to slow down. So if you can't do it, again, yeah, trust me, don't do what I did. So if you can't enqueue the message, what do you actually do? The actual big payload in the message, what do you do instead, right? And so really, this pattern is actually really simple. What you're going to do is pick some cheap, fast storage mechanism that's available to you, and if it's Azure, that could, Blob storage is an excellent use case for this. Any of the NoSQL stuff, right? Cosmos, Mongo, awesome for this. What you're going to do is enqueue the blob somewhere in this cheap, fast storage, and then really you're just going to pass. You're going to get a reference to it, and depending on what technology you're using, that reference might look different, but it's generally something that's like a GUID or a URL, and that reference then becomes the claim check. And so where they got the name for this one is like, imagine you had a suit of luggage in an airport, a really heavy piece of luggage, and instead of like carrying it everywhere that you needed to carry it, you left it in one place. You got the claim check, and then you just walked around and handed the claim check to everybody that needed to do it, right? So then not everybody needs to carry that 50-pound bag around. All they're carrying is the claim check. And like I said, usually a GUID or a URL or something similar to that. So a little bit more like advanced concept for this one. This works like even better when you've got a messaging system where you've got multiple hops that are interested in the message or part of the message, but maybe not the whole message, right? So they need to like say, well, it's cool. I need to know that this thing happened, right? This event happened, and maybe when it happened, right? Like patient A had a CAT scan at this time and date. That's all maybe one of your receivers actually needs to care about. So don't make him like handle the 100 megabyte CT image, right? And let the downstream, when the radiologist finally gets it and needs to actually look to see if you've got something bad going on, let them handle that at that point in time. Like I said, NoSQL and Azure, awesome. This is only a lightweight caveat, to be honest with you. I mean, there of course are going to be additional latencies when you're reading and writing this, but it's not going to be nearly as bad as the one if you're trying to pick it up and put it on the queue a bunch of times. All right, so that is claim check. All right, now my favorite architectural pattern, at least in terms of for the purposes of this talk. So this is the eventual consistency pattern. And this one, like I said, we had patterns at multiple levels. We kind of were talking more design and code level stuff up until now. Eventual consistency is an architectural level pattern. So many systems that we work on, and I would venture to say that it's actually most systems that we work on, are designed to be strongly consistent. And I know that, a lot of folks probably are really familiar with this term, and I've found that a lot of people just are not, because it's just the way we build systems, so we didn't know that there was a name for it. But there is this continuum of data consistency. And so what does strongly consistent mean? That means if you have multiple replicas of a database, for example, at any given time, the information is exactly the same. For all intents and purposes, a reader could read any of those copies of data at any point in time, and they would always be exactly the same. They're strongly consistent. And this was like really, really beat into us right back in the old days, like with SQL, especially where 99% of our data stores were SQL based, right? The ACID properties of SQL, if anybody remembers that, right? What does the C stand for? Right. So it was, this was the way. It was like if you weren't doing this, you were doing it wrong, right? So it was beat into us. Well, it turns out that fast forward a couple decades, and when you're building a massive geo-replicated cloud-based system, this becomes a problem. And not only, I would go so far as to say it makes it impossible, right? You cannot have strong consistency guarantees across the globe. If your application is big enough to have to run in 40 data centers across the globe, if you're designing in a way that all of your data has to be strongly consistent, you will fail. So think about there's a couple, there's lots of use cases for this, but think about social media, another one near and dear to my heart, connected vehicle. So in the social media aspect, right, you're going to have a user, somebody you're following on Twitter or something equivalent to that's posting a new tweet in Germany, right now, and you might be refreshing your page and saying, well, I don't see it. Ah, now I see it. Whereas a guy who maybe was 5 miles down the road from him saw it immediately, or what looked like immediately. Yeah. Everybody always, a lot of non-technical friends always ask, how do they build Twitter? How do they build Twitter? Uh-oh.
It'll eventually get to the rest of us.
Yeah, it does. See it? It's a good, yeah, that's exactly right. You'll start seeing this pattern everywhere. Once you see it, you go, man, this happens all over the place, right? Whether they were like intentionally doing it or not. So, there's lots of questions that come up around, you're trying to update data in lots and lots of places and lots of data sets. You're worried about availability. You're wondering about a catastrophic event, right? And you're worried about just intermittent downtime, right? And for those of you, I'm sure a lot of you guys build Azure systems, the downtime is real, but a lot of times it's transient downtime, right? That was like the get out of jail free card that Microsoft invented 10 years ago. It's a transient error, right? Transient error. Nobody ever said that before, but now they play it, and they're like, it's transient error. Try it now.
It goes away once we fix it.
Mm-hmm. Transient. The product group, you never get them to admit that they broke something. It was transient. It's cool. Yeah, so long running outages. I told this story when we were building we're working on the connected vehicle system, and we're working with the Chinese Azure data centers, which are hosted by a third-party company, right? Because the way 21 Bayonet, they're called, the way the Chinese government works, you have to be a Chinese-owned company in order to operate the data centers, which is the main reason Google doesn't exist in China, and they have Baidu instead. We had a literal fire in the data center. Like, we always talk about like putting out fires. We have a fire drill. No, we had an actual fire, and it destroyed like a good portion of the data center and lots of racks of servers that were running our stuff. Right? So we were certainly glad that we had a backup data center in that was the Shanghai data center, I think, and we were running in Beijing as well.
It was transient.
But they're all transient. It just depends on how transient are they, right? So anyways, so what's the solution to this, right? So, I have a quote here from my old friend, I use that term lightly, Uli Homan, some of you guys might know him, but from Microsoft, where he told me, Greg, applications must lie. And it sounded cooler in his German accent. But so what does that mean, right? That's sort of a flippant way of talking about it. But what that actually means is that massively scalable applications like Netflix, like Twitter, have to present information to the user that they don't know is necessarily the latest and greatest information. They're not intentionally lying, right? They're just being like flip about it. But you're also saying, like, is this the truth? Like, I don't know. It might be, but it might not be either. But try it in a few minutes and maybe I'll have the truth for you. So how do you actually implement this, right? And the concept is super simple, like a lot of these patterns. It's that in the old ACID, right, remember two-phase commits in SQL and all that stuff, where it's like everything had to commit or everything had to roll back, right? That's like the exact opposite of what this is. This is you've updated one source of truth, and then those updates roll out through the rest of the infrastructure, sort of at their own pace. And that pace can be kind of dialed in depending on your application, how you've built it, what your requirements are. But it's as simple as that. Like when you have a connected vehicle, you have a Ford vehicle, when that thing gets provisioned, when it's turned on for the first time, it's going to have a home data center that it connects to, right? And so that data center, when you're the telemetry control unit in your car is sending telemetry, it's always going to go to the same place unless it goes down and then you got a backup. But generally you have like a home data center that it connects to. But somebody else could have the Ford app that's connected to your vehicle, but they're out in California or they're in Brazil or wherever, right? They need to still be able to see, like, did I get a vehicle health check alert? Right? But they won't necessarily get it immediately, right? They'll see the telemetry some period of time later. And there's like I said, there's lots of dials and knobs that you can twist on that. So the whole idea is that because these updates are rolling out, they eventually become consistent. Thus the name, right?
Yep.
Yeah. So cool stuff. This is like a super cool, like an aha moment for me back when I first learned about this stuff, right? Does it really, and you ask yourself as you're designing the system, does it really matter that a user in Europe doesn't see your tweet for 30 seconds after somebody in the United States? In a perfect world, we want it to always update immediately, of course, but does it really, really matter? And as with most things, simple concept, not so simple to implement. So how do we do it? they're also, when you're thinking about from an architectural perspective, a massively complex application doesn't have just one data set, right? There's lots of data domains that you're building out. It's extremely common that each one of those data sets might have a different consistency requirement. So some of the data, right, the tweet data, cool with it being eventually consistent. Maybe even really slowly, because the faster you do it, the more expensive it is. Maybe even really slowly consistent. But in terms of like identity information, like your username and password, probably want that more closely tied to the strongly consistent side. All right? Banking, one of the things I was talking about in this in terms of banking information, right? But a dirty little secret the banks really wouldn't describe it this way is that your checking account, any deposit accounts are actually eventually consistent. Right? You all logged into online banking during the day and you see like the pending transactions. That's eventually, it's not strongly consistent at that point. It doesn't become strongly consistent until nightly batch posting that happens in, at midnight or overnight, right? And that's money. So if the banks can do it, probably you could do it. And so really the whole spirit around this one is like arming you with a different model for thinking about data in your applications, right? You might be working on an app and you go, man, we will never need this. We run in one data center, we got one database, right? But do you always know that? What if you have like some massive popularity spike, right? And all of a sudden, like, yeah, we used to just run in US East, but we found that people in California were getting like unacceptable latencies. So we decided we wanted to move, we wanted to also run our app in US West. You're going to definitely wish that you thought about your data in a different way. And then and again, this talk could be an hour. Each one of these topics could be. There's some tools to put in your toolbox, right? And I think the gentleman in the back, this is where you were heading, I think, right? So there's a few concepts that you should know, like how do we actually like implement this stuff? And item potency is one. And this is a word that it's weird, but I think we stole it from the math guys, but it's now sort of a computer science term. Has anybody ever heard this term? I know you guys know what it means? Yeah. It's a goofy word, super simple. It just means if you do an operation one time or you do it n number of times, the end state is always the same.
Just means repeatable.
Yeah, repeatable, but with an immutable end result, right? So the same result every time, right? So really, if you think about like maybe an example, so if you're thinking about doing a SQL insert statement, can you make a SQL insert statement idempotent? You absolutely can, right? You have to like assume that you're checking to say, if I had done this insert before you do it, if I do this insert statement, what would the state of the data look like? I need like a clue or a hint around it, and if I see that, I'm going to assume I already did it. Somebody else already did it, and I'm not going to do it. Right? The way to guarantee idempotency sometimes is to actually not do the operation anymore. But you have to build that in. Right? It doesn't. In some cases, it comes for free, depending on the technologies. But in other cases, you actually have to engineer it. But start thinking about your operations in terms of making them idempotent. There's all kinds of goodness that comes from that. Think about like from a queuing system perspective. We have this idea of guaranteed delivery. We've been talking about guaranteed delivery and exactly once delivery in the queuing world for what, 40 years? It's a myth, right? Especially in cloud world. You can't do exactly once guaranteed delivery in the cloud world. It's absolutely impossible. Right, the MQTT spec that a lot of IoT systems rely upon has a QoS level, QoS2 that is exactly once. Right, when in the old days when IBM made these big honkin' message brokers, and it was like a closed system, it could guarantee I only did this once because there's only one of me and I know what I did, or I should know what I did. When you start looking in massively distributed systems, when all of the vendors, Amazon, Google, Microsoft, implemented their IoT broker, it's not a broker, but they call it, it's a broker. All of them independently came to the same conclusion that it can't be done, right? So if you try to enqueue an MQTT message with a QoS level of 2 and throw it in an IoT hub, it will puke. It only supports at least once delivery. And how do you do at least once? Make them idempotent. Then you also if your stuff can, and if you can get to a full level of idempotency, you don't even have to do deduping anymore.
So idempotency is basically is this record already in there before I insert it?
Mm-hmm. It could be, right? I mean, it depends on what the call is, right? But yeah, absolutely. It's a really simple concept that like I'm going to try to figure out that I've done this already, and if I get another message that says I should do it again, I either don't do it or I do it in such a way, like think about like an update statement, and maybe you're updating, you know, an address. Does it really matter if it is already the address? Maybe in your system it doesn't, right? Like, yeah, I've just stomped over the same thing with the same thing.
But isn't that the purpose of the upsert statement?
Yeah, upserts, that's exactly right. An upsert is idempotent.
Okay.
But not all databases support them, right? So again, depending on what it is that you're building, this might be easier or harder. But absolutely, that's a great point. Compensating transactions. So again, I think probably most of us have at least a little bit of familiarity with this, but this whole idea is that, you know, if you've got updates that are rolling out eventually, you're going to have stuff like a lot of times, like down that chain of updates, something bad's going to happen. There's going to be some node that can't get itself in a state that's actually healthy. And then, but there might have been, you know, anywhere from 1 to 1,000 other nodes up the chain who've already updated themselves. And so in the old days, we would have done a two-phase commit, right? And we'd have went, bam, dot rollback, and we're good to go. Well, can't do that anymore. So now this is hard, right? Compensating transactions, doing this properly is hard. But what you actually have to then do is figure out, well, I know what the state was before I did this latest thing, and now I have to do something to compensate for it and make it look like it did before. And not easy, not awesome. Data partitioning, this is probably like the one that, you know, even in your smaller on-prem system, still think in terms of how to partition the data, right? Don't make it so that like there's one place that every reader and every writer of your system has to compete at all times for, right? Think about in terms of like, how do we slice this horizontally? Right? And all of the, you know, any cloud-based technology, any data, you know, cloud-based data technology is going to give you tools to do data partitioning. So, but you have to think about it. It's not like something that happens for free, because you can get this wrong and then you screw up all like the performance of your application gets all wonky and stuff, because now you've actually made things worse. You're trying to make things better, but you actually made them worse. So lots of really, you know, I think interesting complexities here, but cool stuff. And I would encourage you like to even think about these principles when you're building smaller. If you're, you know, not everybody's going to be building the next Twitter. Nobody, somebody will, because when Elon runs it into the ground, there's going to be another one. Maybe it'll be us. Maybe we'll do it, but probably not. But that doesn't mean that that these principles can't also be applied to you know, less complex applications. All right, so I could talk about this one for hours. And there's lots of platform capabilities in Azure, like I said. Like, so the role model for eventual consistency is like NoSQL databases, right? So Cosmos DB has all of the Geo Replication goodness all built into it, right? So if you want to like dip your toe into like, how do I build something like this? Building a, you know, using Cosmos DB is a great way to start. All right, how are we doing on time? Okay. Cache aside pattern. So you came here for my, oh yeah, go ahead.
So the last two, when you talked about a queue,
Yeah.
the whole time, and now you're talking about Geo Replication. So what's that mechanism?
That's an excellent question. So if you think about it, I need pictures, right? The main feedback we've gotten, we need more pictures in the next, the next iteration of this. And so think about like, okay, picture a globe, picture data centers all over the place, picture like a data set within the data center, and then it's going out to each one, you know, it's flowing out to the world. But you know what's in front of each of those other replicated data centers? A cube. Oh. So the patterns fit together, right? All right, so here's my hot take. This is what you came for, right? Caching is good. But, that's a joke, by the way, right? I think we can all agree that caching is good. Maybe not Mike, he's grumpy. But doing caching well is actually trickier than it might first appear. And especially if maybe you don't have really deep expertise in all the things that can go wrong when you do it wrong, right? And so one of my former colleagues way back when said, all caching implies policy, right? It's not as simple as just, yeah, I mean, there's an API call that lets me push this thing on the cache. Well, we're not thinking about the policies that govern that piece of information that you put on the cache. You're going to get some really like unexpected and very hard to pin down defects. Has anybody here ever had to debug anything because of faulty caching? Yeah, of course, right? It's either there when it shouldn't be, or it's not there when it should be. And so getting the expiration and eviction policies right for your data is not, sometimes it's like sneaky, like, yeah, it seems obvious, right? Until you actually test with it and your user acceptance testing crew comes back and is like, oh, man, I don't know what the heck is going on here. And then the stuff ends up getting evicted, and you're going back and looking at the state of the server and going, well, like the state changed from when the tester was testing, and then the repro steps are all out of whack. So we tried to like tell a story here, right? Sometimes the cache should be treated as eventually consistent, right? Sometimes the application should treat it as like a source of truth. I go to the cache and I know I'm going to get the right thing, but there are other times that it should be like, maybe I'm going to get the right thing. I'm not going to like assume I'm going to get the right thing. And so that's exactly where the cache aside comes in. So people talk about caching as if it's just one thing, right? And the mechanics of it are largely one thing, but the patterns, there's actually a whole bunch of patterns, right? And you're probably using these and just not knowing that there's like names for them. Right? And so we picked off just one. We picked the cache aside pattern to talk about here because it does play into the eventual consistency that we just spent a lot of time talking about. So better known and known in the past as lazy loading. And I'm sure almost everybody's heard that term. And so this is dead easy, right? So the idea around the cache aside pattern is that the application goes and checks the cache first, and with the full expectation that the data it's looking for is not actually there. And if it's not, then it goes to the database, gets the real stuff, comes back, puts the real stuff in the cache, and has now made the cache strongly. Now we've gotten to be eventually consistent. The system's now consistent as a whole. But that's, and I don't know percentage-wise, like if this is the most common pattern, but, oops, sorry. So contrast this with the other patterns that you may have used that are really strongly consistent caching patterns, like right behind, right through, where the cache and the database collaborate basically on saying, I am always going to be I'm going to be in a consistent state, right? We're in lockstep. Like anytime the database updates, sends a notification to Redis. Redis goes through and updates the data, and then the application goes, I have a one-stop shop, right? I'm going to the cache. And if the cache doesn't have it, I'm going to assume it doesn't exist, right? So two very different ways of thinking about it, but it's all caching, even if you didn't like think about it in those terms. All right, I'm going to try to skate through these last ones fairly quickly. These ones are a little bit again. So now we're kind of again stepping down maybe toward to the design pattern level. So what are the problems, right? Distributed systems, obviously failure is the transient fault thing. I make fun of that a lot, but it actually does happen all the time, right? Like you're connecting to an Azure platform service and it's not working. You didn't change a thing, and then all of a sudden it starts working. And it happens all the time. And in terms of, stating the obvious, developers are generally more focused on the happy path than they are on the exception path. So what are some things that we can do to like mitigate these kinds of unexpected situations? That's really the well, maybe not unexpected, but exceptional situations. Right? That's really why we grouped all of these together. There's this concept of the circuit breaker pattern, right? And this was actually a new one to me a few years back. I had never seen it implemented quite like this, and it actually had come to think good things about it. So really think about protecting or when you're making a call to an external API, especially something that you don't control. This is like really like you've signed up with a third-party vendor and you're consuming their API. It's going to have, you have no idea. They might have uptime guarantees and SLAs and all that stuff, but it doesn't mean that they're always going to meet them. So there's a rule in what we do that says, if a downstream system is having problems, probably the least helpful thing we can do is continue to hammer it, right? How about now? How about now? How about now? Are you okay? Okay? Where's my data? Where's my data? So there are techniques that you can use to not just endlessly hammer the downstream system. And one of those is implementing a circuit breaker. And there's no magic here. This comes from the circuit breaker in your house, right? When things are good, the circuit breaker is closed, right? And current's flowing through. But if it determines that something bad has happened, what does it do? It opens, and no more current can flow through there. And that's exactly the same pattern, right? You've got a client that's making HTTP calls of an API, and it's sending them, but there's this circuit breaker that's protecting it. And if it determines that something bad is happening, it pops open. And then then it doesn't even try to hit the endpoint anymore. Now, the devil is in the details. How does the circuit breaker know that something bad is happening? And what does something bad mean? Right? And for your endpoint, those can all be different things. Right? So it's very easy to say the HTTP 500 is a bad thing. That one we know, all right, that's bad, right? Timeouts, probably bad, maybe transient, but 5 timeouts over a 2-minute interval, probably bad, right? So depending on how you implement this, you can get super sophisticated. I think we talk about it here. You can get super sophisticated with it, right? And you can do, there are frameworks out there that allow you to implement circuit breakers, and you can declaratively list okay, if I get this number of errors or these types of errors over these intervals, that will open it. And then there's the idea of, okay, all that's well and good, but when and how does it get closed? Right? In our house, we just go and we try it again, and it pops again, right? We try it again, okay, something bad's happening. And that's also a legitimate way that you could use, a code-based circuit breaker. But again, this will be different based on your implementation. Some of it, if it's bad enough, maybe it actually sends an alert, and production support, DevOps guys have to actually look at it and go, yeah, this thing we're trying to call is having serious problems, and we need to shut it all down. Or maybe it's time interval based. We're not going to send any more calls to this, whatever credit bureau monitoring API that our mortgage app uses. We're not going to send any for 5 minutes, but then at 5 minutes we'll close the circuit breaker and we'll try it again. So again, most of these patterns, simple concepts, but how you implement them can be really interesting. This is one we definitely want to. When we revise this deck, we want to see some more code examples, right? We want to talk about how does this actually work. But it's all really about protecting your system and by protecting the downstream system. And so all of that really goes hand in hand with retrying. So everybody would retries are good, but how many retries are good, right? Not infinite. That's certainly not ever good. And especially if the system's already having trouble, man, hammering it probably is not going to make it better. So the industry has settled on this pattern of retry with exponential back off, right? Which sounds so fancy, right? All that means is you're going to agree upon the number of times you will retry a given call, but you will essentially double the interval that you wait between retries. That's the exponential part, right? So you might say, I'm going to retry 5 times, and I'm going to start with a second. So thing fails, wait 1 second. Try it again, fails again, wait 2 seconds. Again, 4 seconds, 8 seconds, 16 seconds. And once you get to 5, it's gone. But again, for your system, that might not be appropriate, right? 10 might be appropriate. 10 with, starting with a 10 millisecond retry time. If it really is transient, maybe it's good the next time. So I don't want to make the user wait if I think try it now. Okay, good. That actually does happen a lot in Azure too. And then there's this whole other discussion around the class of errors that you're getting, right? If you're getting a 404 or something, that's does it matter if we retry it 1 million times? It's probably never going to work, right? So why not? In certain systems, you might short circuit the retry altogether based on the type of error that you just got. So all good stuff. It's really just in terms of thinking about ruggedizing your API by protecting it and protecting downstream systems. And along those lines, throttling, right? So this is actually a pretty interesting statement, right? We talk about the cloud. The cloud gives the impression of infinite resources. And I mean, for all intents and purposes, I mean, for most of us in the systems we build, an individual Azure data center will have essentially infinite resources. They're, I mean, just ridiculously massive. Unless you're provisioning VMs, that's a whole nother story. But the reality is, even though they are infinite, let's say, for all intents, that doesn't mean they're free, right? So you might have infinite volume, but I'm guessing you don't have infinite money, right? And we've all, I mean, anybody who's built Azure systems, anybody build an Azure system and not once been bitten by your bill, and went, oh man, that was a lot more than I thought it was going to be. We all, I mean, if you haven't done it, you haven't been trying hard enough. So yes, we can scale out as much as we want, but should we? So the whole idea that when you're building an API, right, you want to be protective of it because it might be a public-facing endpoint, number one. Number two, you might be selling your API as a product. And most APIs as a product don't tell the people that buy them, hey, hit this as much as you want. Like, maybe if you have a cost model for that, but generally almost all of them have some, SLA that's enforced. Where it's like, for this much that you're paying me per month, you get this number of calls over this interval, right? And so then you've got to figure out a way to then enforce that. And so some of the throttles might be like cumulative throttles. You can have this many total requests over this time period. And other ones might be concurrent throttles, where you can do as many as you want, you just can't do more than 5 per second. Do it for as long as you want, but just not more than that. And so there's lots of ways, again, the details are the important part, but there's lots of different ways to actually achieve this. And take advantage of the Azure platform capabilities if you can, right? Like API management is awesome at wrapping your APIs and allowing you to do throttles based on configuration, but sometimes that's not enough. Sometimes you actually have to do some of these other things where the degraded quality one is interesting. These are actually fairly hard to implement, but they're possible, right? Where you're saying, yeah, I'm going to do it, but I'm going to be slow. But I'll get it to you when I can. The load leveling, like we talked about, then it's like, hey, send me as many as you want. I'll let you know eventually that I did it, but send me as many as you want. And then this one is pretty interesting, the defer operations, where like, yeah, I'll get to it, but only when I think it's okay for me to do it, right? It's safe for me to actually perform this much, whatever, IO, whatever, this much processing. And that, depending on your SLA, that could be 5 minutes from now, it could be 2 days from now, right? Just depends on your business case. Whew. All right. So that's a lot, right? So we'll wrap up quickly. One of the things, so I mentioned at the very beginning, there's a million patterns out there. We listed some of the ones that were like candidates for us to put in this that fell out for one reason or another, but all good ones to learn. And there's more, right? So it's not a definitive list. And so just kind of circling back, right? Start thinking in terms of these patterns in general, right? Chances are the problem that you're trying to solve at any given point has probably been, if not fully solved, at least thought about by somebody before, and probably also solved many, many times. So, go out there and take a look. And there's some good, good old school resources online, of course. The well-architected framework is good. The Microsoft Cloud Patterns website is awesome. Some of Fowler's stuff is still applicable. Some of the enterprise integration patterns are still applicable, but I'll leave you with a caveat. Be careful, because this topic is old, right? It's like as old as Mike. And so there has been a lot of stuff written and produced and evolved over time, right? So old guys like us like to talk about the Gang of Four book. Everybody knows who that, maybe what that is, right? Eric Gamma's book. That was like the Bible on design patterns, written in the early 90s, late 80s. Don't read it. There's no reason to go and buy it unless you want like the geek cred of just having it like on your shelf behind you on your Zoom call. Geek cred. Yeah, right. Like we our old school reference material. The examples are in Smalltalk. If anybody does anybody remember Smalltalk? Yeah. So and C++, but 100% outdated. And the reason for that largely is that a lot of the patterns that they talk about have become first-class features of modern languages. Right? We don't need the decorator pattern anymore because we've got decoration semantics in C# and Java. Right? That's just one example. So there's a lot of like clickbaity as we were doing searching and stuff, like, oh, the top 8 design patterns every developer should know, right? Like, I don't know. All right, take it with a grain of salt, right? We used to go through this thing back years ago where you would say, you're doing a code review or a design review and you're saying, well, I use this pattern and this, I use the mediator, I got the decorator, I got the memento, I got the chain of responsibility. And that meant my design was good. And I'm like, oh yeah, I used 9 patterns. Like, no, you still might be crap, right? So it doesn't, in and of itself, you can still do all of the patterns wrong, right? You saw how complex all this stuff was, and we just started talking about kind of the caveats and trade-offs, right? So proceed with caution, but go to trusted sources and talk to people about it, and yeah, enjoy. Hopefully, I've given you at least a healthy curiosity about this space. And I know a lot of you folks are probably know more about this than I do, so I appreciate you listening to me. So do we here's contact info, LinkedIn, QRs, and all that stuff. But I know we're probably actually over on time, but we're good. Can somebody get me a Michigan State score update? Anyway, anybody questions, comments?
Comment.
Yeah.
While you're talking about the circuit breaker pattern and all that, I was reminded of the first place I learned that, which is from the Poly library, which is a .NET library.
Poly is
if you haven't checked out Poly yet, you really ought to. It's awesome, part of the .NET Foundation. And,
Yes, absolutely. Poly is like the de facto standard for doing circuit breakers. So, unless it's like use it unless you have some really compelling reason not to. Yeah. Don't try to rewrite all that logic yourself if somebody else has already done it. Yeah, good point. All right.
No questions.
Where are you down?
.NET Foundation is probably a good reference to go to anyway, because a lot of the patterns are baked into their libraries. So.
It is, man. Microsoft's been talking about patterns and practices, right? The PMK group. I don't even know if it's still really around in its current incarnation, right? But they invested heavily in that for many, many years. So, yeah.
MSU is up, by the way.
Say again?
MSU is up, by the way.
Nice.
Is the eShop on containers app, the reference app, does it employ some of these patterns?
I think so. Yeah, I haven't looked at it lately, but generally, yeah, I would think so. That's a good question. I'll look into it.
Well, Greg, that was fantastic.
My pleasure.
Another round of applause. Another round of applause. Raise your hands if you want some free.